Okay, folks, thanks for being patient yesterday. And I know some people, some of us were kind of frustrated by maybe my lack of clarity on how to graph these polynomials, and maybe feeling some frustration with how quickly our brains forget this stuff. We did a Desmos activity trying to get the feel for how these polynomials work, and we took a quiz yesterday in sixth period. We're going to do a quiz retake on how to graph these polynomials. But look, polynomials. Why are we trying to graph them? Why are we doing that? Well, today and yesterday we had inequalities. So if we can get a picture of what the polynomial looks like, and it says when is the function greater than 0, it's as simple as this. Here all these values are greater than 0, and then you say, well, what x values generate that part of the curve? It's these x values between 0 and 1. Now the only challenge left is to say, do I use open brackets or close, brackets, or open circle, closed circle, all that kind of stuff. And really we're saying greater than 0, so we'd say between 0 and 1. And in interval notation it would look like this: between 0 and 1. That's not an ordered pair. That's saying x is greater than 0 and less than 1. Now that's not the only interval where it's greater than 0. It's greater than 0 over here as well, so you'd say also greater than 2. So we would switch and say, I switched to black. I didn't really need to say that. I would just say x is greater than 2, or in interval notation it would be from 2 to infinity with a parenthesis, right? And we'd want both of these, so we'd put a little union symbol between them, union symbol between those two. I hope I'm making that clear, how easy it is, if you can see the graph, to analyze the function, to make conclusions about the function, right? So how do we get better at analyzing these graphs? Without technology, what are some things that we're expected to understand? So here's a polynomial. How do I know it is? How do I know it's a polynomial? Well, it's not being divided by x, right? The ones that are divided by polynomials, like a polynomial divided by polynomial, look like this. They've got vertical asymptotes, and you've got functions that are tending toward those vertical asymptotes, and you've got horizontal asymptotes. Not always, sometimes we do. And the function tends down toward the horizontal asymptote. It's end behavior. We're going to do that in video number 2. So video number 1, I'm just trying to focus on these guys, polynomials. Polynomials are smooth. They don't have any holes in them. They don't have any asymptotes. They're just nice and smooth functions that you can graph without lifting your pencil and without making any super sharp corner turns or anything like that. Okay, so what are some steps? I don't know if I've ever given you guys just step by step with polynomials. We did some work with them. We did some work on Pearson with them, but just graphing them by hand, I feel like we need a little bit more work and maybe some more structure. So determine the end behavior of the function. So end behavior is kind of a weird thing. I've got a picture of what the author says about end behavior, and I forgot where I put it now. It's over here. So let me zoom in on this guy right here. End behavior has to do with this leading term. Okay, so if the whole thing was just expanded, the term that's going to run the show, dominate this polynomial, is the leading term. So you could just pretend like it behaves just like whatever that leading term is at the ends. That's called end behavior, okay? So let's do this. Instead of analyzing this part of our homework last night, this inequality, let's do the quiz problem that we did yesterday, okay? And I'm going to start by graphing this guy right here. And to determine the end behavior, what I need to do is I need to really kind of imagine expanding all this, multiplying out x plus 2 times x plus 2 times x plus 2 times x minus 3. I don't think you heard me say that you really have to multiply it out. I said imagine we're multiplying all this out. When we have an x times an x times an x times an x. That's going to give me four x's multiplied together. So our function's leading term is going to be 1. I'm going to emphasize the 1, so you don't have to write the 1, but I'm going to write 1x to the 4th. Would we have a lot more other stuff? Absolutely we would. And we had to do this expansion in some of our homework problems. And it was a pain, right? It was so easy to make a mistake. But here's the good news. You don't have to get every term over here. You only have to focus on the first term. Now, an x to the 4th polynomial, if it was just 1x to the 4th, you really, just by visual, can't really tell the difference between x to the 4th and x squared. It looks like a parabola. So do you notice at the ends, I'm going to highlight the ends are going up on both sides. If it was a negative 1x to the 4th, it would be going down on both sides, okay? So on our graph, you know, when you're trying to graph these things, step 1, what I would do is I would go over here and I would put an up arrow on the left and I'd put an up arrow on the right. We might have to move these out or move them in depending on how our scale sets up on the x-axis and where our x-intercepts are, but I'm not too worried about that right now. I'm just saying I got my end behavior down. Maybe I'll emphasize that in red. Okay, we got this arrow going up and we got this arrow going up over here. Okay, so that was one of the things I looked at on your quiz. Do you have up arrow, up arrow? Okay, and that's because we had an x to the 4th. If we would have had an x cubed here, then it would look like a cubic function. It'd be going down on the left, it would be coming up, and it'd be going up on the right. Okay, now it says find the x and y intercepts of the graph. Boy, when it's in factored form, man, x-intercepts, super easy. Okay, so x-intercepts are where the factors equal 0. So like where x plus 2 equals 0, you move the 2 to the other side by subtraction, you get negative 2. It's where x minus 3 equals 0. You move the 3 to the other side and you got x equals 3. These are my two x-intercepts. Let me go over here and put them on my graph. I think I had one at negative 2, so let's say negative 2 is like here, okay? And then I had one at 3, so let's say 1, 2, gosh, hope this looks decent. 3, okay, so I got my two x-intercepts on there. Let's see, what do we got to do now? Oh, we got to find the y-intercept. Y-intercept's not too hard either. You're plugging 0 in for x, okay? So the y-intercept is where you've got 0 plus 2 cubed times 0 minus 3. Let's see, 2 cubed is 8. 8 times negative 3 is negative 24. And so I'm going to go over here to my y-axis. Oh my goodness, if I'm counting those as ones, I don't have to make the scale over here the same. I could say like this is negative 10, this is negative 20, and then I'd say like negative 24 maybe like right in there, right? Now, this has me a little worried because we said the end behavior is up on the left and up on the right. I got to get to this x-intercept, I got to get to that x-intercept, and I got to get through that y-intercept. Boy, that has me a little nervous right now, but let's look at the next step and try not to get too worried about it. It says determine the zeros of the function and their multiplicity. Now, it's kind of weird because an x-intercept is the same thing as the zeros. So let me make a little note of that. It's kind of weird that the author says find the zeros because we've already done that work. It's right up there, right? So there are my two zeros. Now, the multiplicity is important. The multiplicity on the negative 2, let's look at what that means. It means what's the power on the factor that is generating that x-intercept. So the multiplicity on negative 2 is 3. So negative 2 has a multiplicity of, I didn't spell that right. You got the idea. Multiplicity. I'm missing some letters in there. It's that word right there. Of 3, right? Okay, so what does that mean? It means, because it's an odd, it means that it's going to cross through the x-axis. Okay, so at negative 2, it's going to do something like this. Well, remember how the arrow's up here, right? And we're getting down to that y-intercept, so I know it's going to cross like that. It's not going to cross like that because the arrow's not down over here, right? So ultimately, I'm going to have to connect from that arrow down to this x-intercept because there aren't any other points over here, right? So we're going to get from here down to there, and it's going to keep on going down, right? Okay, so let's go to the other one. What's the multiplicity on the x minus 3 factor? The x minus 3 factor right there has a 1 on it, right? So here we go. So 3 has mult, I'm just going to abbreviate this, mult of 1, which means, I should put like an equal there, which means it crosses again, okay? If it was an even, it wouldn't do this, it wouldn't cross over, it would come down, touch, and go back up. Okay, so this is a touch, this one was a cross, right? So both of ours are crossing, both of our x-intercepts are crossing here. So if you had it touching and going the other way, like if you had it coming up, touching and going down, or coming down, touching and going up, you're missing that part right here about multiplicity, okay? So I don't want to jump the gun here. I'm feeling pretty good. I think I know what this function looks like, but let's do the rest of the steps. It says, determine the maximum number of turning points. The maximum number of turning points is 1 less than the degree of the polynomial. The degree equals 4. Okay, let me put that up here. Degree equals 4, which is giving us those end behaviors, but it also tells us that the turning points at most, I'm going to put at most, equals 3. Okay, that means, like, you know, it could come down, it could turn again, it could turn again, and then go back up. Do you see that? Like there's 1, 2, 3. It doesn't have to have that many. Like it could look like this, right? A fourth degree polynomial could have just 1 turning point. So that's what we're trying to figure out, or at least, you know, on our graph we're going to consider that. It's not, I don't think, the most helpful piece of information that we got. Okay. Step 5 says use all the information. Now I'm going to make a graph. It says find additional points. It also says worry about the scale, which I've kind of already done, right? I said, shoot, man, we got to fit negative 24 on there. So I can't be counting by ones like I did on the x-axis. So I think I have enough information, or at least, you know, to put a rough sketch down. I got to get from that arrow down to this guy right here, and it's got to get all the way down here, and we want to make it look smooth. Oh boy, I'm going to have a hard time making it look smooth. Do I know if it turns right here? I don't really know that. I mean, it could turn like over here somewhere, right? But from you know, I could make it look like it turns over there. I don't really know where it turns or how many turns it exactly has without doing a little bit more research, right? And so now my end behaviors are good. I'm going through the x-intercepts the way they should go through. I'm going through the y-intercept, and I don't have more turning points than are possible. Okay, let me show you a way that would be completely wrong to graph this function, okay? So let's say somebody didn't really take into consideration the turning points, and they said, well, okay, so I got all my key points on here, and I don't like really where that guy is right there. I'm gonna move this dude over here. Okay, so let's see. Ooh, that makes it larger. Hold on. Let's move it a little bit more like that. Okay, so let's say somebody said, I'm going to come down here. I'm going to get through here. I'm going to do a couple wiggles like this. Come down here. I'm going to do a couple wiggles like that just because I'm not sure. That wouldn't be okay. There's way too many turning points on this thing. Okay, at most this thing has 3 turning points. So, you know, don't overdo it. You know, you could just cut right through here if you want, and then keep on coming up. How would we find the minimum value? Well, that's where calculus would really come in handy, and we don't, you know, have a whole lot of experience with calculus. So other than that limit stuff that we did with difference quotients. So for now, this is the best that I think we can do. I mean, this little turn right here and little wiggle here is unintentional. I wouldn't count off for that. All right, I hope I'm making this clear on how to graph a polynomial. They should be nice and smooth. Now, let's try that with a homework problem, okay? So I'm going to run through this one real quick. I'm going to put a graph down, and then we're going to try to answer the questions about, you know, when is it greater than or equal to 0? So determine the end behavior. Well, if I expanded this, it would be an x squared. If I multiplied an x squared times a negative x over here, right? I'm not worried about any of the other multiplication. I'm just worried about the ones that's going to generate the largest degree, which is going to be a negative, right? Because there's a negative x over here. I'm going to get a negative x cubed. That means the end behavior is down on the left and up on the right. Okay, so let me put a little sketch of this thing. Here's the way I would do it. I'd put a little arrow over here. I'd put a little arrow going down. That's my end behavior. Find the x and y-intercepts. Okay, well, my x-intercepts are -4 and +1, because if I stick a +1 here, I get a 0. If I stick a -4 over here, I get a 0, right? And the multiplicity, I'm going to kind of come down to this one. X equals -4 has a multiplicity equal to 2, which means that it touches. And at x equals 1, it has a multiplicity of 1, which means it crosses, okay? So let's go up here and put like where we think -4 is going to be. And let's put over here where we think 1's going to be. And I'm going to come up from the bottom here, and it's going to touch, and it's going to, oh geez, this doesn't look all that great. It's going to touch, and it's going to come back down, okay? I haven't determined my y-intercept, so if I come up here, y, if I stick 0 in for x, I would have 4 squared, and then I'd have that times 1, so I get 16. Oh no, that doesn't seem to jibe with what I was thinking. Like, how could this start down here, come up, touch, and go back down? I've got to get up to +16. Ah, I forgot one thing. See, this is where, like, coming down here and checking this stuff really helps you out. My arrows are going the wrong way. Because it has a negative x cubed, it's going to reflect it over the x-axis, and it's going to go up on the left and down on the right. So I got to make some modifications here. This is not the end of the world. I'm not going to get too frustrated. I'm just going to say, oh, hey, that was kind of helpful to know that the y-intercept is +16. That means I got to come down, I got to touch, I got to go up, I got to get through 16. Let me put my other end behavior on there. And then I got to get back down through x equals 1 and try to get over that arrow. Okay, so next thing I'm going to do is I'm going to try to answer this question. Where is f of x greater than or equal to 0? So it's all of these values that are greater than or equal to 0, including the endpoints. So I would answer that question between -4 and including -4 all the way over to +1, because that's this value right here, square bracket. I would switch to the back of the book. I would find that answer, see if that made sense, if I've answered their question correctly, you know, if I need to make some modifications, all that kind of stuff. Do you notice I didn't even worry about turning points? I think like this step is a little unnecessary and not that helpful. Man, I hope I'm making this clear. I love you guys. I know you can do this. Don't get too frustrated. All right. Thank you.